So, welcome to this video in which we will continue seeing some examples of complex manifolds. But before we do that, I'll just make some comments on the implicit function theorem and inverse function theorem, which will be helpful in finding more examples of complex manifolds as complex submanifolds of already existing or other complex manifolds that which we already know about. Okay, so for example, let's start with the inverse function theorem. So this is an holomorphic version of the inverse function theorem. And let's say that we have a function defined in an open set in Cn to Cn that is holomorphic, and its derivative, so this matrix, this complex matrix for ij from 1 to n is non-singular at 0. Okay, so these are the assumptions, holomorphic, and this matrix is non-singular. So this is like an holomorphic version of, or anti-holomorphic version of the Hessian. Okay, so it's kind of like a complex Hessian. And then the conclusion is that there exists a neighborhood of 0 contained in U, such that the restriction of f to that neighborhood, which I've called V here, so the restriction of f to V is invertible and has holomorphic inverse. So invertible and holomorphic inverse. Okay, so it's kind of like an analog. It's really like an analog of the inverse function theorem in the smooth case, where you would have invertible and with derivative, and so this is an analog in the sense that we do our guarantee that the inverse is holomorphic. Okay, so the idea of the proof is basically to apply the usual, first put ourselves in the condition where we can apply the usual inverse function theorem, and then that will give us the first conclusion, and then we prove the second conclusion by direct computation that this inverse is holomorphic. Okay, so let's first start with putting ourselves in the position where we can apply the usual implicit function theorem. For that, I'm going to write the function f as an n tuple of functions, so these are the components, and with each fij as its real part plus imaginary part, which I respectively call uj and vj. Then I can regard Cn as R2n and f as a map from R2n to R2n, or a domain in R2n to R2n, and we can write its Jacobian in this way. Okay, so this is the standard Jacobian of f viewed as a function from R2n to R2n in this manner. And the Jacobian is then a linear transformation from R2n to R2n. Okay, so now we can complexify it by simply looking at the Jacobian, and instead of considering as a map from R2n to R2n, we take a tensor product with C and we extend it by C linearity. Okay, so then we get a complex linear map, which I'll call the complex Jacobian, from C to n to C to n, which is just the tensor product of R2n with C over the real numbers. And we can write this in another basis of Cn, which is the DDZIs, which I'll call that basis. And in that basis, the map can be written in this way. Okay, so so I'm using that basis both in the C2n of departure and the C2n of arrival. Of course, at arrival, it's going to be really to be some other coordinates, not the z's, but some w's or something. But that's where the ones to which we are mapping the corresponding fi's. So in those coordinates, the complex Jacobian looks like this that I've written here. And in particular, in the case when f is holomorphic, then df phi dzj is equal to 0, and so is df phi bar dzj, because that is just the complex conjugate of this first one. Okay, so these anti-diagonal guys there vanish when f is holomorphic, so these guys are both equal to 0, and we are left with this. Okay, so that is the complex Jacobian of of my transformation. Okay, so that's the complex Jacobian seen as a C-linear map from C to N to C to N of an holomorphic function. Then if we want to apply the inverse function theorem in the usual case, we better guarantee that the Jacobian of our function, seen as a real function, is actually invertible, so non-zeros. For that to happen, the determinant needs to be non-zero, and is enough that the determinant is non-zero. So that's what we are going to do here. So here we look at the determinant, and using this formula here that I had alluded before, the determinant is just the product of the determinant of these two matrices, but one is the complex conjugate of the other, so that's the norm square of the determinant, which is greater than 0 by assumption, and therefore we can apply the usual inverse function theorem. Okay, so that is true. Okay, so final usual inverse function theorem, and that guarantees the existence of the open set V on which f is invertible. And so this is the restriction of f to v that is invertible. And now we must check that the inverse is indeed holomorphic near 0. So in order to do that, we shall write for any z the coordinates zj, and just by the fact that z is equal to f minus 1 of f of z, then we will write fj for the j coordinate, so we can write zj is equal to fj minus 1 of f of z, so that's what I had written here. And now we are going to differentiate that with respect to zi bar. So that is the trick. The trick is to do that and apply the chain rule. If you do that and you remember that f is holomorphic all along, then you finally arrive to just this simple formula here, which is basically the matrix multiplication of this holomorphic piece of the Jacobian of f by the anti-holomorphic piece of the Jacobian of f minus 1. Okay, and now you remember that by assumption this guy is non-singular at 0, so it is non-singular near 0, and in all of v because of the invertibility. And therefore, or by possibly shrinking v, it will be non-zero near 0. And therefore, this guy here, for this all to be equal to 0, this guy here must vanish. Okay? And for that guy to vanish, then f minus 1 needs to be holomorphic. This is basically the definition of f minus 1 being holomorphic, the vanishing of this guy. So saying this is the same thing as saying that f minus 1 is holomorphic. So that was not very beautiful. Okay, slightly better. Okay, so now let's go see some consequences of this computation before we go to the implicit function theorem. So the first consequence of the computation was an intermediate computation we did, that the determinant of the Jacobian is the norm square of the determinant of these dfi dzj. Okay, and under our assumptions this was greater than 0 near the origin, but for a general holomorphic map we just get that this is greater or equal than 0. So once this proves that in the case when they are greater than 0, that one-to-one holomorphic maps must preserve the orientation, because there is no way the determinant of the Jacobian is going to be a negative number. Okay, so that's the key point. So holomorphic maps preserve orientations. Okay, so now a piece of nomenclature which I had already mentioned before briefly is that an holomorphic map that is invertible and whose inverse is holomorphic is called the biholomorphism. And before we proceed, there is an important thing about holomorphic maps, bijective holomorphic maps, which is that they are always biholomorphisms. Okay, is a biholomorphism. So I wrote this incorrectly. Is a biholomorphism. Wait. Okay, so that is what I wanted to say. And of course, this is not true in the infinity case, and that is what I was alluding to here. Okay, because see, in the C infinity world, you can have a map that is bijective and smooth, but whose inverse is not differentiable. And the standard example is the map x goes to x cubed, which is obviously bijective and from R to R and smooth, but its inverse is not differentiable at 0. So x to the 1 over 3 is not, the cubic root is not differentiable near 0, right? Because it would look like something like this, right? It would have infinite derivative there if it had anything. Okay, so let's see now the implicit function theorem before we see the applications of these theorems to finding complex submanifolds. And the implicit function theorem basically says that the holomorphic version of it, that if we have an open set in Cn and a map to Ck, then I'm going to suppose k is less than n. And I'm going to suppose that the derivatives of this map in the first k coordinates in C, so here I have z1s up to zn are the coordinates here, and the map f is f1 up to fk. And now I pick the first k coordinates here, and I'm going to construct this matrix dfi dzj. So it's the same matrix as before, it's just that I'm restricting it to, it's like a matrix, a minor of the Jacobian, okay, of that complex Jacobian I've mentioned before. And I'm going to denote this map by not this one actually, sorry. And so that is dfi dzj is non-degenerate. Then there exists an open set containing 0 and contained in the domain, and a function that is holomorphic from Cn minus k intersected with V. So this is, if V is an open set in the origin, I haven't made a picture, but let's say that V is an open set in the origin like that. And we have here Cn, and this is Cn minus k, and this is Ck. Then V intersects Cn minus k is basically this region here, okay? So we have a map from there to Ck that is holomorphic, so to Ck, this part here. And it has the following property. The function f vanishes at a point if and only if I can write the first z1 up to zk coordinates, which are these ones here, in the image of the holomorphic map from the remaining ones, which are down there. Okay, so you can write it. You can write as a consequence this equation here, and the proof is very simple to the one before. So let's write it in this way by simplicity. The conclusion that we have from the standard implicit function theorem. So we use the implicit function theorem to guarantee the existence of such a W, that then we need to prove it's holomorphic. And to prove it is holomorphic, we basically differentiate this thing with respect to ddz bar for all i's. And you doing a computation and using the non-degeneracy of dfi dzj near 0, we conclude that these guys here must vanish. That these guys here must vanish, which is the condition that dwk the wk's are holomorphic, which means the w is holomorphic. So that is the proof. Just to mention one more thing, that you have to remember in proving this, remember that the Fj are holomorphic. So you need to use that also. Okay, so just add that there. And before we continue, let me just make a note on notation. If I have a map from Cn to Ck, I'm going to denote by df the n by k matrix, which is dfi dzj for I equal to 1 up to k, and n and j equal from 1 up to n. So it's a rectangular matrix. And I'm going to call rank C of df its complex rank. Okay, so the complex rank. And then the condition, for example, that this guy here is non-degenerate, you can actually, up to not having to rearrange the coordinates to write this slightly more generally, you can write that instead as saying that the rank of df is k. Okay, so and then this plus f holomorphic, then these conditions implies that f minus 1 of 0, which is a subset of Cn, is the image, or locally the image of a map W from Cn minus k to Cn. Okay, so that's what this means. Okay, so and this map is holomorphic, of course. Okay, so now let's go to our application to see what complex submanifolds are. So a complex submanifold of dimension n minus k of another complex dimension n complex manifold is basically a complex manifold of dimension. So I forgot to write manifold here. It's basically, no, sorry, this is correct. Sorry, I was just reading badly. So a complex submanifold Y of Xn of complex dimension n minus k, so that's part of the definition, is a subset of Xn, which is locally given by the image of a maximal rank holomorphic map from Cn minus k to X. Okay, so this means that for all points y in Y, you can find an open set in X containing Y such that the intersection of Y with that open set of X is the image of a holomorphic function from Cn minus k to X whose rank is maximal. Okay, so basically the idea is like that. So if you have X, let's say that this is X, and you have Y here, it's a subset, then you can find around the point little y in Y, so that's little y, you can find an open set V inside X such that V intersect Y is this thing, such that V intersect Y is the image of an holomorphic map from some open set. So this is U inside Cn minus k, and you get that, so that is the map, and the rank of phi of d phi over C is n minus k. So here I should have written d phi. So one way to find such guys is to use the implicit function theorem. So let's say that you look at y, subset in Xn, such that is locally given as the zero set of holomorphic maps of maximal rank. Then the implicit function theorem tells you that they are a complex submanifold of dimension n minus k. So that's what the implicit function theorem tells you. Okay, so being locally the zero set, locally given as the zero set of holomorphic maps of maximal rank, means exactly what I've written below, means that for all points y and I, there exists an open set containing them, such that the intersection is the zero set of a map from V to CK that is holomorphic. So it means that in this picture, if you add, for instance, a function f to CK such that V intersect y is equal to f minus 1 of 0, then it means that you will be able, for f with maximal rank, of course, with rank of df equal to k, then it means that you will be able to find the stuff in blue for all points in that open set, v intersect y. Okay, so that is what the implicit function theorem tells you, that you will be able to find the blue stuff. Okay, so an example of this is the case of hypersurfaces. So if you pick a complex manifold and an holomorphic function from X to C, which has 0 as a regular value, so that means that the rank of df is equal to 1. So here I'm going to put curly df to 1 everywhere. Then the pre-image is a complex submanifold of dimension n minus 1. So this is usually called a complex hypersurface. Okay. So there are some particular cases that are more easy to write down. The first one is perhaps the easiest, and it's a direct application of this, which is the case of affine hypersurfaces. So affine hypersurfaces is basically you pick X, the big manifold, to be Cn, and you pick an holomorphic function in Cn with 0 as a regular value, then it's the pre-image of 0 is what is called an affine hypersurface. Okay, because it's a complex hypersurface of Cn. So another example is the case of CPN. And remember, CPN is Cn plus 1 minus 0 quotiented out by C star. And now, instead of looking for functions in CPN, we are actually going to look for functions in Cn plus 1 minus 0, whose zero set descends to CPN. So in order to do that, what we are going to consider is a polynomial, an homogeneous polynomial, sorry, from Cn plus 1 minus 0 to C, or from Cn plus 1 to C. And we are going to suppose that 0 is a regular value. Now, the condition that the zero set descends to CPN is basically assured by the condition that we have picked our polynomial to be holomorphic. Because every time you pick an equivalent point in CPN, a point in Cn plus 1 minus 0 that will go to an equivalent point in CPN, then the function just scales, this polynomial just scales by a power of that function. K is the degree of the polynomial. And therefore, at this point, it is the function, the polynomial is 0 at this point, if and only if it was 0 at this point. And so this zero locus does descend to CPN, and this is called a projective hypersurface. Okay, so a particular case of interest is the case of complete intersections, and those can be a complete intersection in CPN could be obtained also in the same manner, or in CN in the same manner. But in general, if you have a complex manifold, and if you have k functions from x to c that are holomorphic, with 0 as a regular value of the function to ck that is given by combining all of them into one function, so this function over there, then the intersection of the zero locus are called a complete intersection. So in generally, locally, everything will be a complete intersection, but globally need not be. And complete intersections are global complete intersections. Okay, so okay, thank you for the attention. Until the next video.